Greetings. The first law of thermodynamics is a very, very strange equation. It looks very simple and straightforward in the first sight. Nevertheless, if we look at it carefully, we would note that it is doing something which is very unusual. Uh, it's unusual to add apples to oranges. It's unusual to add things that are very different. Now, here, just assume, just imagine what it means that it is adding heat transfer, which is due to a temperature difference, to work, which is due to a pressure difference. It is just adding the cooling of a teacup with lifting that teacup. It is adding elevation with velocity, and that's just change. It is adding things that are very different. In the British units, heat transfer had dimensions, had units of BTU. Work had units of pound force foot. So this just showed that how different the two are. And those who use British units usually multiply either of them to get an equivalent value of the other. SI, system of units, basically is showing us that work and heat transfer are the same as far as the first law of thermodynamics is concerned. Of course, the second law shows us that heat and work are different things, but still, first law adds them together, although they are different things and have different effects. The problem I want to solve now just uses this equation and sees how interchangeable could the different effects be. The problem I want to solve is just about a pump. And the pump that we want to talk about is usually drawn like this. We usually draw a pump like this. This is I and this is E. This is the pump inlet and also the pump exit. Now, it says that the pump is adiabatic, so Q equals 0. Now here we add work usually, so there is work that is added to the fluid, and so the energy of the exit fluid would be higher than the inlet fluid, and we don't want to lose this work to the heat to the surroundings. So it's an adiabatic pump, and it says that PI, which is the inlet pressure, is 70 kilopascals, and TI equals 300 kelvins. These are the inlet pressure and temperature. The exit pressure, PE, equals 350 kilopascals, and the problem tells us that only 0.05 Kelvin is added to the temperature. So it is basically telling us that TE is 300.05 kelvins. That's what it says. Well, it says that first of all, for the first condition, ignore velocity and elevation or changes in velocity and elevation. Ignore changes in velocity and elevation. Two, it asks us to draw the problem on a diagram. It usually pays to find the best diagram which could express the problem better than any other diagram. It helps uh, the person who is solving the problem to know the best diagram which represents the problem. Third, calculate the specific work. Four, calculate that if it were to replace a pressure increase to a velocity increase, how much velocity would we gain? Could we gain? So if it was to replace pressure increase with, with an increase in velocity, what speed would we gain? What would the exit velocity be? And five, if it were, if it was to replace pressure increase with elevation. It means that instead of increasing the water pressure, if we were to raise water level to some height, say fill a tank at some level, then then what elevation could we expect? Okay, these are the five questions this problem has put in front of us. And what we should do is to simply do all the five steps, take the five steps that we always do for problems. What were the five steps? I just repeat them. First, find properties. Two, draw a diagram. Which the problem has also requested. Three, simplify the conservation equations, and more important, do all this, do all above, do all above for the control volume or for the boundary you have drawn, for the control volume or the boundary under study. And 5, collect everything, collect all towards the solution requested. So these are the 5 steps that you have to take just to get all these requests of the problem. So what I do first is to decide on the control volume, which would be the pump. As simple as that. There is work added to it, but it says that Q equals 0. And that means that the pump is adiabatic. Now we have all inlet and exit conditions, and there are many ways that we could approach finding different properties. Usually, drawing a diagram comes hand in hand with finding properties. It helps us very much to know where the points are in order to select the correct path to find the properties and find the approximations. So, what we do is to draw a diagram, and since pumps are pumping liquid, then we are in the compressed liquid area. So what we do is to draw a diagram just like before of the saturation line. And the point is this, that on the saturation line, of course, the constant pressure lines look like this, but in the compressed liquid area, the constant pressure lines are extremely close to the saturation line. I mean, even what I'm drawing here, even what I'm drawing here is an exaggeration of the distance. The distance is even closer. So to find the properties on a point like that, which has higher pressure than the saturation pressure of this temperature, this, call it this T sat, for this constant pressure line, it's very easy to use the saturation to use the saturation liquid properties. So for points on the compressed liquid zone, so for, I write it here, for compressed liquid, for compressed liquid properties may be approximated properties may be approximated with saturation, saturated liquid properties with the same temperature. So if you need a specific volume for this point, just it would be very as good to read the specific volume of the saturated liquid, and that would be as good for a specific energy and for a specific enthalpy. All would be the same. It would be very good to just read the saturation properties. But what happens for a pump? I mean, I can't draw a line here. So assume that the pump is here and then pumps a liquid to here. It's very difficult even to draw it because the points are extremely close to each other. And the pumps don't change temperatures that much. So if we read the saturated values, I mean, look at this problem. It says that the change in temperature is 0.05 Kelvin. Delta T equals 0.05 Kelvin. So it would be very difficult to just read the values here, just read the values from the saturation line, even interpolate them at such close proximity and expect good results. But for the problem at hand, we are given that the change in temperature is 0.05 Kelvin. Later on, I will teach you a way to just calculate work of a pump from a different way, perhaps at the end of this problem. But as it is, what I would do is to just use the values we are given and try to find proper values. You see, these are the values we are given, and now I would try to find properties for these values. So for the incoming fluid, I, we know that T equals 300 kelvins and P equals 70 kilopascals. I use an application to read the properties, which you can find many applications for cell phones. Just go to Google Play Store and see those applications that are available. The results I found was that V equals 0.001 cubic meters per kilograms, H equals 112.64 kilojoules per kilograms, and U equals 112.57 kilojoules per kilograms. In the compressed liquid area, H and U are very close since the specific volume is so small. Okay, and for the exit condition, T equals 300.05 kelvins and P equals 350 kilopascals, and therefore you would read V equals 0.001 cubic meters per kilograms. Of course, if we go to if we extend to further decimal points, then there would be a difference, but that would be a very, very small. We usually can ignore it. Okay, H equals 113.1 kilojoules per kilograms, and U equals 112.75 kilojoules per kilograms. These will be the values that we can collect from just an application if we don't want to go and read values or interpolate saturated liquid values from the tables. Still, we can do that, and the numbers would be very small, and that's the advantage pumps have because they can increase pressure with very small work. The work you need would be far smaller than if you wanted to increase pressure in the superheat line. In the superheat area, if you want to increase pressure, you have to do far more work than what you have to do here in the in the compressed liquid area. So what we do is to write down the laws, the conservation laws, mass conservation and energy conservation, and try to simplify them for the problem at hand. This is the problem at hand. I would put it just here to remind us what the problem was and try to simplify the conservation equations for this very controlled volume. Conservation equations are the mCv by dt equals m dot I minus m dot E. And since this is a steady flow problem, this term vanishes, and the conclusion is that m dot I equals m dot E and equals m dot. Now, the energy equation would read dE Cv by dt equals m dot I times hi plus vi squared over 2 plus jzi minus m dot E times he plus ve squared over 2 plus jze and plus q dot and minus w dot. This term vanishes, and for the time being, and we have ignored changes in velocity, changes in altitude, in elevation, and therefore, and we divide everything by mass flow, since mass flow is constant, and therefore the outcome would be 0 equals hi minus he, and heat transfer, the problem is said to be negligible, and therefore minus w. Remember, all dimensions in this equation would be kilojoules per kilograms. The dimension in these equations are kilojoules per second, which is kilowatts. Here we have divided. You know that kilojoules per second equals kilojoules per kilograms times kilograms per second. This is m dot, this is h, And this is m dot times h. This is kilowatts, this is kilojoule per kilograms, and this is kilograms per second. Remember to follow the units very, very carefully. Now, we have, of course, HI and HE, so we may just write W. Work, specific work, is HI minus HE, and that equals 112.64 minus 113.1, and that would equal minus 0.46. The minus sign tells us that we have to do work, which is correct. For pumping a liquid, we have to do work on it. So this is minus 0.6 kilojoules per kilograms. That's the value for the pump work. Okay, now the problem is telling us that if instead of increasing the pressure, we were to give velocity to the fluid, how much velocity could we get? So what we do, we say that if instead of changing HI and HE by changing the pressure should remain the same. Nevertheless, the velocity should increase. So there will be some VE. VE will not vanish. I write this second condition with green just to show that it doesn't vanish. We keep this term. So how much velocity could we expect? And the answer is this. If it was, there would be no increase in pressure. So for the second case, T would equal 300.05, but P would still be 70 kilopascals. 300 kelvins. Now, for this case, we again read the properties, and H equals 112.85 kilojoules per kilograms. V would be again 0.01 cubic meters per kilograms, and U would be 112.78 kilojoules per kilograms. How would we simplify? First law. This term vanishes. This term and this term vanishes. This one we should keep. There is no heat transfer, and of course there is work. So instead of simplifying like this, we would find 0 equals HI minus HE minus VE squared over 2 and minus W. So there is some velocity at the exit point. Now, just replace values. We have done the same work, but the work is not spent on increasing pressure. The work is spent on adding to the velocity, giving some velocity to the exit flow. This is like what you find in some boats. Speedboats use strong pumps just to give velocity to the water, and they use that reaction to go faster. This is just the same thing. So VE squared over 2 times 1000. Remember, please, there should be 1000 here because V over 2 is V squared over 2 is in joules per kilogram. It is square meters per square seconds, which is equivalent to joules per kilograms. And just to get kilojoules per kilograms, which is the unit we usually use, we should add 1,000 here. This equals 112.64, which is the inlet enthalpy, minus exit enthalpy, 112.85. The difference is because we have kept that 0.05 kelvins as the temperature difference, and plus, which is minus times minus, plus 0.46. And the outcome for VE would be VE would equal 22.36 meters per second. So that's the velocity we would get at the exit if we use the pump, we use a different pump, not the same pump. We use a different pump that instead of adding to the pressure would give us more velocity, would increase our velocity. Now the third question, which is as interesting, is how much elevation did we get? If we didn't want velocity, what we wanted to pump water to a higher tank. How much elevation do we get? If we did that, then this term would remain, and this one and this one would vanish, and these two would be the same as these two, because we are assuming that the inlet and exit are the same as the second case, but instead of adding to the velocity, we have to add to elevation. So the first law would look like this. 0 equals hi minus he minus gz minus w, and this would be the first law. Now the work is spent on increasing elevation and not changing the h and not changing the velocity. So replacing values, z times 9.81 divided by 1000. Please don't remember this because z times 9.81 is in joules per kilogram, and just to keep consistent with the units, we have to divide it by 1000. This equals 112.64 minus 112.85 and plus 0.46, and Z would be 25.48 meters. So we could raise the water level to 25 meters just with the same pump, but if we didn't try to increase its pressure. Of course, when we are taking this, the end of the control volume, remember, if we are taking this, the exit plane would not be here. The exit plane, we would have raised the water level to Z equals 25.48, and the end of our control volume would no longer be here at the pump exit, but it would be here because the exit condition, as we are writing in this equation, has a different elevation than the inlet condition. In the early stages, in the starting case, we just use the same elevation. Here, we are changing the elevation and using a different elevation. Good. So, a very simple conclusion is that, you see, you have the first law. Please concentrate on this equation. We have the first law, and everything has to balance. The work we do, I just draw a line around it just to make it clear here. You see, this is the first law, and everything has to balance. So if you put work in it, it has to show itself in one of these terms. Either it has to show itself in Q, there has to be heat transfer, or which we saw this in our previous example on a turbine when we saw that work could show itself as heat transfer or not. Or it has to show itself as delta H, which could be delta T or delta P, could be delta V, a change in velocity, or it could be a change in elevation. All of it is very possible. And if there is none of these, all of these remain the same, then there must be some heat transfer to balance the work we have done. Or the problem would not be steady state. So the pump would heat up, say. You see, the pump would heat up, and I mean, if we just use an adiabatic pump, and um, don't make any increase in any adiabatic, and none of these change, then this couldn't be zero, and the pump would heat up, would be warmer. That's uh, the only thing that can happen. Um, I At the end of this problem, I just use a small note from the second law of thermodynamics. In the second law of thermodynamics, you are taught, or you will be taught, that work for a pump for a controlled volume, the reversible work for a controlled volume, which is the minimum work for that controlled volume, may be calculated from an equation which is minus VdP. This equation, you see, when we had another equation, W equals integral PdV, which was only valid for cylinder piston arrangement. This equation was only valid for a changing boundary. For a control volume, for a reverse, both are for reversible or semi-equilibrium processes. Both are for them, but this is for a system, for a changing volume system, often used for a piston cylinder arrangement. This one is for a controlled volume, just like the pump that we used. Now, for this equation, we may write, because V remains constant, this is a very useful equation for pumps because V remains constant and makes calculation very simple. So the answer would be 0.001 times the change in pressure, which would be 350 minus 7. And the answer we get from this is minus 0.28 kilojoules per kilogram. So the ideal pump, which could do such duty, would need a work 0.28 kilojoules per kilograms instead of 0.46 kilojoules per kilograms. And what they define is the isentropic efficiency, which is 0.28 divided by 0.46, which finally would be 0.609, which is quite usual for a pump to have 61% efficiency. This is called the isentropic efficiency. And if you have not yet learned the first law, the second law of thermodynamics, then it's a good point, it's a good hint to look for this calculation when you are reading and learning the second law of thermodynamics. Well, thank you very much for your attention and cheers.